it loops forever till it finds the answer, okay? So what we do, so I put the star, you understand, and this is the next step. I read it, then I describe, assign A the best attribute, assign A a decision attribute for node. For each value of A, create a descendant out of node. Sort training examples by leaves. If examples perfectly classify, stop. Else, iterate over the leaves again. So, write it down because we don't have it in the slides as, if you want to write it down, as I want to, when I'm describing it, I want to refer to the different steps of the algorithm again and again. Okay, so as I said, we loop it forever till we find the answer. And the first thing is we are picking up the best attributes. We have defined what is the best attributes, but today we will see in more mathematical form how we can define the best attributes, okay? And then after we have defined the best attributes, what we do, we start to split it, right? We will start to split the decisions that we have, or the attributes that we have, in order to make some decisions based on decision we may assign a few more nodes. So, after we have our best attributes and we have decided what are the values, what we do, we look at the answer and we are assigning, we are picking up another attribute. And we continue it like that. How far can we go? How far can I do with these divisions? After we have done the divisions and I'm assigning some values as an output of the first node or whatever node, the ice node, let's call it, I will see if I can perfectly split all my data. If I can do it, it means that, okay, the tree has done its job. So there is no need to iterate, or there is no need to do further division. But if we have not split it yet, then we have to do it. We have to do it again and again. Now, this algorithm that I have written, and you might have copied it, is known as an IDT algorithm. Okay? This tells us how we can find the best attribute and how we can design and establish and build our tree. Now, how can we define the first step, which is the best attribute? Because we understand that everything depends, very much depends on this best attribute. We have done a few games before in previous lectures, and we understood that this and best attributes plays a very important role. Now, what we want to do, what we want to define the best attributes, we want to use a definition which is called the information gain. What is information gain? If you remember when we were reviewing probability, we had some slides which was telling what is entropy in information and what is the information gain. Do you remember what was information gain? What do you think the definition of information gain should be?
Change in entropy.
Forget about the formula for time being. You want to define information gain. It means that for some information, if I'm providing some information, I want to know what is the gain that I have, right? So in general, this is how we can define it. But when we go to the depth of the information, the definition of this information gain is actually a reduction in the randomness. We want to see how much I can reduce in the randomness. Now, the formulation for the gain has been given in this form. As you can see, we have entropy, and you remember we were relating entropy with the randomness. We will get back to this sentence that I said in a few seconds when I go to the next slide. So let's look at this formula and define what it is. The first part tells me that what is the entropy of the S. What is S? What is S? My training set. So, and what is this one? This one is called the expected value or the average entropy value of my training set. Now, I'm talking about the entropy. Why I'm talking about entropy in the formula of information gain? What is the relation between entropy and information gain?
We're trying to reduce the entropy, or we're trying
What?
to see how much the entropy reduces.
Relate entropy and information.
Entropy is kind of random.
If I am calculating the information gain, why I have entropy everywhere? What is the relation between entropy and information? Entropy is the measure of information. Entropy is the information, right? Because imagine that I have a coin, right? I have a coin, and this is a fair coin. If it is a fair coin, what does it mean?
You can flip it and you get 50-50.
Yes, I can flip it, I can toss it, and I can get either a head or a tail, and I know that this is 50-50. Okay? Now, I have also another coin which has two heads. Okay, if I flip it, I will get head. So, now you can tell me that which one has higher randomness? The coin that we have which has head and tail, it has randomness. Actually, this fair coin is called the 1-bit, and it has two heads, it's called 0-bit. Now, this one has higher randomness, higher information, higher entropy. Why? Because before you do the action, you don't know what is your result, right? So this means that this is the whole concept of the randomness. Before you do it, you do not know what is going to happen. You know that we can use the probabilistic model in order to model what is the probability of what something happened. But do we know for sure what will happen? No. What about in the two-headed one? Before you flip it, do you know what is the result? Yes. So, the whole thing is that we want to see, we want to take care of these randomness. So, later in the slide you will see that what happens is that we start from high entropy and we try to get to low entropy. Actually, this is the whole tendency of the world. From high entropy we move to low entropy. So when you have your tree, we start with a very high entropy and we want to go to the low entropy. So what is the best node? The best node or the best attribute is that it gives us the maximum gain. which I can have the highest change, right? If I tell you that I have a node which, if the entropy is, let's put it in this form. If I have a node A, okay, attribute A, and what it does at the beginning, the entropy of the beginning is 0 is equal to alpha. And if I use A, what I get in this level, I get entropy 1 to be alpha over 2. And I have another attribute B, that if I use it, entropy of B will be alpha over 10. Now, you tell me, which attribute is better? Which attribute is better?
First one.
A or B?
A.
Why A?
Because
It's a half of the.
Anton, what do you think?
I think
A. Eric? Martin?
I think B.
B. Why?
Because it divides more.
Look, what we want to do from high entropy, I want to go to low entropy. And I have, if I go to the lower value, it means I have higher gain. Which one is bigger, alpha over 2 or alpha over 10? Alpha over 2. It means that from alpha to alpha over 2, I have less gain when I go from alpha to alpha over 10. So B is a better node. B is a better node. Now, we talk about the entropy is actually the measure of the information. It tells us about the randomness. Actually, what we want to do, we want to talk about what is the formula for the entropy. Do you remember the formulation that we have for the entropy? The formulation for the entropy minus the summation of the probability P log P, right? And what happens is if we have the entropy high, the randomness high, it means that the probability of you be able to say what is the output will be lower. We know what is the output. Remember, there are two things. We know what are the outputs. We know what are the labels. We are doing the face recognition. We know that what are each labels that we have in our scenario. But if I give you an input, or even before I give you an input, before doing anything, you cannot tell me what is the output, right? So it means if we have very high entropy. Imagine I have only one class and only one student and only one sample which can come. Then there is no concept of entropy because the person, let's say, is Anton. So no matter what happens, I have only one person, it's all Anton. It's like a two-headed coin that I have, okay? So, as I said, the whole story is that we start with a very high entropy and we try to go to the low entropy. And we find the best node in the form that when we split, we are reducing as much as it is possible, okay? Now, ID3 was very helpful because it tells us how we can build a tree, right? It tells us how we can build a tree. Because we know that what is a decision tree, we know that how expressive it is, and we know that this ID3 tells us how to build the tree in a very effective form because we had so many forms of the tree. Now there is a question. There is a question, and the question is this. What will happen if we have continuous attributes? Did you notice that till now we had discrete attributes for discrete output, right? Discrete input, discrete output. The question now is that what will happen if the input is continuous? What will happen? What about the output? No, the output is still discrete. Now, do you remember if the output is discrete, what do we call these type of problems? Classification. So we are still in the classification, but my input is not discrete anymore. Right? My input, instead of being, is it an animal or is it a human? Is it a male or is it a female? We are not talking about that one. We are talking about what is the height, what is the weight, what is the age. So they can be a continuous form. So the question is that what will happen if the input that we have is continuous? Or how is it going to work in the decision tree when we have the input to be continuous? And let's make this one a quiz. So think about it. I will give you 1 minute. Think. How do I make my decision tree if the input, instead of being discrete, is continuous, right? Previously, all the trees that we made, we had, is it live or dead? Is it, I don't know, is he or she male or female? Is it human or an object? So all the questions, all the things that we had were very discrete. Is it like short, medium, tall? So it can have multi-attributes, but what happened, multi-values. But what was happening that it was very discrete. Now, right now, I'm not talking if it is short, medium, or high. I'm asking what is the height. So I'm talking about a very continuous value. So think about it, that how the decision tree will look like. If it was discrete, we would draw a node and we would show the values, right? For example, we will ask for the gender and we say that male or female. Or we would consider the, I don't know, let's call it height category. And then we would have, let's say, short, a medium, and tall. So we have like 3 attributes. Now, there can be several answers. One of them is that we can write down all the possible things. Like here we have 3 possibilities, we can write all of them. Assume that we have the height, okay, we have the height, and we are writing all the possibilities. And let's start with saying that a person is 1 meter. What is the next value?
1 meter and 1.
1.001. What is the next one? 1.00, I don't know, 01. So we can see that this is not possible. Why? Because we have infinity value. We have infinity value, so we cannot really draw all those values in there. The second way is that we can look at the data set that we have, okay, and it might help us about the numbers, so we can have like some good understanding. Look, I have 100 people, and these are the heights, so I can have some limited number in here. But what is the problem with that? Yes, that's what Eric says is true. We can reward it in this form. It's okay if I am the value that comes as an input, because the problem is that I'm training and then one value from test comes. The problem is such that this value is out of the range of this one. So imagine that I am training the people on the left side, and then there is some guy there who's very tall and taller than what I have as a maximum value. So what will happen in there? So we can understand that looking at the training will not also give us a very, very good value, good results. Now, looking at the test set, I want to draw the tree. I can look at the test and say, look, I have, let's say, 170, 2, 5, and then I will make the tree height. And I said, okay, I have 170. I'm just giving the numbers. So. And then the other one is 205. And I know that if this comes, it goes to the left, and this one comes, it goes to the right. What is the problem with that one?
You have mixed tested.
This is cheating. We do not touch the test set. We cannot use, although it's labeled, we know it, but we cannot use it in order to train. So we do not mix, as Tavi said, we do not mix the training and the test. So, what about the range? we can actually cover more values instead of having one individual one. Instead of saying that it is 1.001, 1.0001, I can always define a range. For instance, a more meaningful one can be something like this: age, and I can have, let's say, age to be between 20 to 30. And what are the attributes that I can get in here? So what are the values can I get here? It's either true or false. Okay? It's either true or false. So, as I gave you here, in order to, when we are talking about the continuous term, in order to be able to cover much more numbers and be more realistic, we are dealing with ranges. So we say that if it is between 20 or 30. Do you remember that we played the 20 question game? Actually, we had some questions which were kind of continuous. I remember Tavi also asked that one, Eric also asked that question, and the question was that, has the person died before 10 years ago or after 10 years ago? In other words, we cannot specify that did the person die like 10 years ago, 10.1 years ago, 10.2 years ago. But what we do, we are defining a range. Before or after. It's continuous, right? It is continuous form. So, this way of defining is also cheating. Why it is cheating? Because I can always look at my training set and I said, okay, what happens that it seems that I have the people that I have in the classroom are either, age-wise, are either less than 25 years old or above 25 years old, okay? So I can look at that one and define, is the age less than 30 or is it above 30? Actually, this type of cheating, this is good cheating because if you remember, we were used to do this one when we wanted to do the data representation. The most famous algorithm that uses this type of question is the BST. You remember the binary search trees in algorithm and data structures? It checks at each node if you are above this value or if you are below this value, and accordingly it goes, like dictionaries. The issue in here is that the data should be sorted. Now, here is the next question. And it is a true-false question. So I want you to think, because this question will be a quiz question, so I want you to think and come up with a solid answer. If it is true, because, or if it is false, because. And the question is this: does it make sense to repeat an attribute along a path of a tree? Look, the question is this. If I say attribute A, and then if it goes to attribute B, does it make sense to ask again attribute A? This question does not mean this one. If I have attribute A, I ask attribute B here and ask attribute B here. We understand that this is totally different from this scenario. The question is this. The question is the black one. Does it make sense that if I'm asking this attribute, I come back and ask the same attribute? And I want you to think about it for 1 minute before you actually come and answer it. Abdulaziz, did you make your mind?
No.
You say no? Fatima? Say yes? Okay, Abdulaziz. We start with Abdulaziz. Said no. Why do you think no? Then we ask Fatima yes. Why she thinks yes? Okay, ladies first.
I think when we have a comparison with two value and the second one compare with the definition value, it can be.
So you mean that this makes sense if Eric in his questions was saying that, is it alive or dead? And I said dead. And then he says that, is it a famous person? And I say yes. Then he asks, is it alive or dead? Does it make sense?
No.
Or you just said yes?
In not this case, just in the other.
This is a general question.
Maybe I don't know.
Yes, David?
It makes sense when you have continuous values, or you can split continuously.
For example, you say that, are the age of the person less than 25? And then I say yes. And then you say that, is the person male or female? And I say that male. Then you ask that, is the person less than 25?
I can ask like, is the person less than 10?
Now,
But that's
he's saying something which I'm getting back to this point. In general, the answer is no. The answer is no. It does not make sense to do it. However, we can actually increase our gain. We can have more gain if, in case of the continuous variable, if we are asking the question in different form. If we are asking the question in different form. So what Tavi said is very valid. We are again asking a question about age. This was a question about the age. This is a question about the age, but we are asking it in different form. Right? So it's like that, like this. Is the age less than 20, greater than 20 and less than 30? And I say yes. Okay? And I go something else. And imagine the answer is false. And can I ask a question about age to say that, is the person teenager or old? It is about age, and we understand that the answer to this one can actually give me very good information. Why? Because, can you tell me that what is the answer? If I say that, is it a teenager or an old person, true or false? Or let's say teenager and old. If the answer is teenager, what can I understand in here?
Less than 20.
Age is less than 20, and if it is old, so I understand that age is greater or equal than 30. Right? So, same questions about age, but the way that we are representing it, it will be different. But indeed, the answer is no if we are keeping it the same question. If we are keeping it same attribute but different representation, then it's yes.
I actually thought about one way that it would make sense. Like,
yes.
what if the answer is a chameleon, and we ask that if it's red, and then at one point it isn't red, but then afterwards we ask again that is it red, and then it has turned red. So it's chameleon. In that case, it's
We assume we are not drinking and playing, right? Yeah, we assume that one. But indeed, no, it does not make sense is the correct answer. However, the sentence, the question that I asked was very general. If I want to be very specific, I have to consider the situation that I just described and Tavi mentioned. So in the continuous form, we have different strategy. As you can see in here, if the answer is false, then we can ask something about the age in order to get a better description. Now, one more thing. And the question is, in the algorithm that we have here, when do we really stop? In our ID3 algorithm, the question is that when do we really stop? And we understand that in the last slide we have written that when the training examples are perfectly classified, then it means that, okay, this is the stopping point, right? Do you agree? I have a good training and I make a tree in a way that for the training I get the 100% of recognition and classification.
No.
So, no, this is the stopping condition.
It's not very good.
No, this is absolutely good. But the problem is, what if we have noise? So this is the deal. I wish that it was working like that. So this is definitely a stopping condition. The question is that, what will happen if we have noise in our data?
Sample and hold.
Huh?
Sample and hold.
Well, not necessarily redundancy. I can tell you an example is that what will happen if I have two faces of Eric and one of them says, no, this is Eric, and the other one has been labeled as Martin. And when I'm training my tree, I will see that I go to the infinity loop. So this is considered as a noise. So the question is that, when do I stop? One of the other answer can be is that when we have no more attributes, right? So you have your training, you have list of attributes, you put the attributes inside it, and then you do it till the attributes finish. But we understand it is kind of very weak stopping condition. We can have a better one. Why it is kind of weak stopping condition?
Because of the continuous case.
Yes, in the continuous case, we can have infinity values, right? We can have infinity values, so it will not be a very good form. So, then we have to be able, in order to make our system works very good, we have to be able to handle this noise. So let's see how we can handle the noise. So the data can be corrupted, and the possibility of having such data is always very high. So what we do is this. We can always trust our data because we don't have any other alternative, right? I give you the data and you really don't know if it's a noisy data or not. So you have to trust it. But we understand that we can always need to verify our data. Why do we need to verify our data? Because the whole problem of the classification of machine learning was that we want to generalize, right? You make a tree and you want to do the face recognition and you want to generalize and say that, hey, I want to sell it and you can take it to your own country, to your own institute and run it and it will work. And in order to do it, we need to verify our data, or in other words, we have to find out a way that we can handle the noise. Usually what happens is this. We can, I remember one session that I was not here and Pejman was here. He was talking about cross-validation, keeping one of the training set out, train your system and then use that training in order to do the cross-validation. We do the same thing in here. We will keep one of the values that we have out in order to keep what is it called? To test all our systems. Now, what we have here is this. What will happen if I have a training set, I look at my training set, and I make a very excellent system. And for my test set, I get perfect results. But then, when I want to give it away to another institute, to another place to test it, it fails. In other words, I will fail to do a generalization. What was the word that we use for this type of problem? We say that we have an overfitting situation. So what is overfitting? Overfitting means that I model my system, I make my tree, and it works very well with what I have in my hand, but I cannot generalize it. Okay? Let's put it in a very simple form. You are in the chemistry lab and you have measured some values, right? And you have lots of data. And what you are doing with your data is this. Let's see if you remember what was the overfitting scenario. We have our data, okay? Can you tell me that what is the overfitting? If I have overfitting problem in this example, what should be overfitting? What is the overfitting in here? If I want to, let's say, fit a function,
It will go through all of the points.
yes, it will be this. I mean, not necessarily a line, but it goes through all of the values. Let's say this is the function. This is called overfitting. Why it is called overfitting? What's the problem with this one? Because I cannot generalize and say that if action A if I have action A and reaction B, they have, let's say, linear relationship. By using the overfitting, I cannot come to this conclusion. Because I can give you another type of A and another type of B, and I may get this type of data, which I see that this is also linear, but my overfitted function cannot fit in here, right? You can see the problem. I cannot generalize it. This is the problem with overfitting. It fits very well for your current data, and that's it. But whereas, if I say that, okay, this is a line, and I understand that this is a linear equation, although it does not pass through all of the thing, I can generalize it. So, sometimes with the tree, we have also this problem. We have the problem of overfitting. But the question is that, how can I avoid overfitting? How can I avoid overfitting? When do I have overfitting in trees? I mean, what are the reasons? One of the big reasons is that the tree that I have is too big or too complicated. Right? Too big, too complicated means that I am answering all this question, I'm passing through all these points. So, the question is that how can I get rid of the overfitting? As I just told you, one way is that we can take one of the data of the training node in order to do the cross-validation. In order to do the cross-validation to see that whether the tree that we have is ready to be generalized or not. But this can be time-consuming, this can be not easy to do. Usually what people are doing is this. They do something called pruning. Do you know what is a pruning in gardening? You have a very big tree, you start to cut the different branches of the tree because you say, this is about to die, so you cut it off. This does not give any more fruit. Or, I don't know, this one is making, let's say, shadow for other trees, so you start to prune. And although you are cutting, but you are doing it for good. It is for the health of the tree, it's for the, I don't know, increasing your product and all other things. We do the pruning in the decision tree as well. We make the full tree, and then we start to ask this question: what if we collect some of the leaves and back it up? In other words, we said, okay, these leaves, these nodes we can cut them. Like the and or, do you remember the and or? We could have the full tree, and we can say that, this part, we can ignore them. Why? Because I can get to the result decisions without having them. So the same thing is here. We can start to do the pruning. We can say that what will happen if I combine this one or I collapse these parts. Do I get the same results? If the answer is yes, we will do it. Otherwise, we cannot do it. Okay? Now, we have talked about discrete input, discrete output. Continuous input, discrete output. Now what we want to do is this. What will happen if the output is continuous? In other words, what will happen if I am dealing instead of yes, no, true, false question, a question something like this, 2x plus 17. Which means that if I give a continuous value for x, I will get a continuous value for y. Then I remember that this is not a classification problem anymore. This is called a regression. So how do we adapt our decision tree to do this is the topic that we want to talk right now. So we understand, we have handled what is continuous, what is the discrete input, discrete output classification. continuous input, discrete output classification. We have talked about the trees, the noises that we have. We are thinking, we have some idea about how we can get rid of that one. So the question is that what will happen if the output is continuous? So if the output was discrete, maximum gain or entropy was pretty good, right? It's because it was yes or no, I could see, and if it reduced the entropy, it was very good. Now, here, the question is that what is the splitting criteria? What's your name? Jürgen. So what is the splitting criteria in here? What was the question? Maybe you should turn off your computer and continue listening to me, right? So, what do you think when I have continuous output? What is the best splitting criteria?
The input.
Sorry?
Like the input.
You have seen it quite a lot because we have talked about this type of things before. Variance is something that we can pay lots of attention to that one because it tells me for the continuous term how much I am varying. So what is happening, you can look at it from this point. The best criteria is that how I can make between classes, between the answers, the stanza as maximum as it is possible, right? So this is how we are handling the data. Now, before I go to the next slide, let's quickly see what we have learned today. We have talked about the decision trees representation, and this is something that we are inheriting from previous lecture. We talked about the ID tree, which is a top-down learning algorithm. We have seen before in the last week that how expressive the decision tree is, and it is something that it caused the overfitting because it's very big. And what are the best attributes? We saw that the gain of information is very important, and we have seen how we can deal with this overfitting. Now, and we are continuing in the sense that we have now the continuous output, and we saw that this is what's called regression problem. This is a regression problem. And the regression is known for us as mapping continuous input to the output to the continuous output. So we have continuous input, mapping it into the continuous output. In general, when we say regression, regression is this, from a psychological point of view, it's like this. I am very sad, right? And I start to sit at a corner, and I get back to my childhood, right? So this is called regression. This is how we have the regression. Now I want to do an example to tell you that why this true meaning of regression is related to this regression that we have. Right? So in order to do that one, we have an example. We have a picture of me and a picture of an average person. Okay? So a picture of me and a picture of an average person. And we have this question. Assume I have kids. And the question is that what would we expect my kids to look like? In other words, are we expecting to have my kids to be of the big size as I am? Or on the average size as most of people are? Or something in between? Now this is a very serious question, and I want you to make a quiz. Think about it for about a minute. This is me. I have big size, you can see. And now this is an average person. Assume I have kids. The question is that, will the kid, of course we are talking about the adult kid right now, will the kid be like me, big size? Or will the kid be on average size? Or will the kid be playing with a mobile phone, have something in between?
probably more like an average person.
Average person, okay. Martin?
More like your size.
My size, okay. He is what?
English.
Yeah, he is.
Something in between. Like,
Something with you. We had three choices.
because
and three.
you could have children with someone that looks like yourself, so you have higher probably being that or
Practically, the middle class answer is a correct answer. In other words, the person, my kid, will be something between me, and between an average person. Because what happens is that from data point of view, if you look at it, I, as a big size, is actually a noise. What is the meaning of mean? The mean means that, okay, everyone was like me, but some people came and disturbed this mean. Right? That's why that we have the variances in the data. But what happens is that because in my some ancestors were mean, and I am of my ancestors, what happens, my kids will be something in between. Because they will inherit what they had from the ancestors and what have from me, so they will be away from the mean, but they will also be away from me. Because this is something that in genetic they call it, it's actually regresses to the mean. In other words, it goes away from me and it goes towards me. If you are very tall, the average is short, your kid will be towards the average. You can come up with hundreds and thousands of examples. So that, look, the person was tall, taller than the average, and the kid was taller than the father. So this type of example exists, but the tendency is that we are regressing to the mean.
Isn't weight a really bad example? Because
We assume that no one is overdosing and everything goes like, we understand some people are genetically fat.
yes,
And
the environment has more effect.
no, yeah, then, well, okay, let's make it tall, because I wanted to use myself not to be offensive, and I didn't find myself tall, but within the class I found myself quite fat, so I used the size. But the whole issue was that if I am a noise, the tendency is it is regressing towards the mean, and that is the reason that we are using the word regression. That's the reason that we are using the regression, because we want to see, we will see that the value that we will calculate it is regressing towards the mean. So what we have to talk, in the next session we will talk about regression as a function approximation, and we will talk about linear regression. So when we formulate it, you see how it is related. But the question, one other thing that I want to talk about, and it was about the previous topic before we fully close the decision tree, was this. We said that in decision tree, the best attribute is the attribute which is kind of maximizing the gain, right? Maximizing the information gain. And do you remember I think it was either last week on Tuesday or the week before on Friday, we had an example, which I showed you an example, and we had 3 graphs. Do you remember? And the graph we have green and red dots. It was something like this. We had a graph. It was positive and let's say negative, and one of them was this. The other one was this, and the other one was this one. Now, and we said that this is the best because it is splitting us fully into what is it called? Perfect classification. 2 classes, one is positive, one is negative. Let me put everything is the same. And then there was this fight that which one is worse, and I said that actually both of them are worse, even this one might be worse than worse. Now that we have learned the gain, the information gain also. So what we do is this. Here we understand that what is happening to the information here? What is happening to the randomness? Completely separable. What does it mean, the randomness? If I am in here, do I need to think whether I am positive or negative? No, I know already what it is, so there is no randomness. Well, when I come to here, I can see that there is absolutely no change in the information. In other words, if I am from here, when I come into this point, do I know what I am? No, I don't know. What about in here? I will be exactly the same situation as the previous one. Although number-wise I have been split, but when I am here, I absolutely have no idea if I am plus or minus. And in this specific example, we understand that probability-wise, there is no change of probability then, right? So we see that we are not reducing the entropy. So again, from this gain information point of view, this is the best node or attributes that we have, and these two together are the worst. So that's why we said that really we cannot say which one is 2, which one is 3. Both of them are kind of number 3. So we will continue by talking about the regression. We don't talk about the decision tree anymore, and linear regression, and we will continue accordingly. Do you have any question? If you have no question, this is the end of the lecture for today, and see you next week, on Friday.